Hi everyone. So if you don't know me, my name's Jade. I'm a postdoc at Swinburne and I'm going to talk about gravitational waves and cold collapse supernovae. So one of the reasons why I think supernovae are so exciting for gravitational waves is that they could potentially be the first gravitational wave source that we observe electromagnetically and also in neutrinos and also with gravitational waves. So we've seen supernovae with EM and neutrinos before, and we've seen gravitational waves with EM, but not all three at the same time. And we can't detect gravitational waves at the moment to a very far distance away. So if we find a gravitational wave signal from a supernova this year, we'd probably also see an optical signal in my favorite optical detector, which is my own eyeballs. So there's lots and lots and lots of challenges to detecting gravitational wave signals from a cold collapse supernova. So the first one is that it takes me about 3 months to make a 1 second long gravitational wave signal for one supernova. And supernovae have loads of complicated physics, and we all have different codes that don't always agree on the results. And so currently, there's no way we could take every possible supernova and calculate all the possible gravitational wave signals like we do for, say, binary black holes and do some kind of template-based search because, we just don't have the computing power for that. And the gravitational wave signals also have some stochastic components. So this is a typical gravitational wave signal from a cold collapse supernova where this is the time and this is the frequency. And they usually all have this typical rise in frequency with time. But these little lumps along the mode will change if you simulate the same explosion twice with all the same setup. Then because of the stochastic processes, these little lumps along the mode are going to change, and the phase will be stochastic. So that's another additional detection challenge for us. So current searches for supernovae make minimal assumptions about the source morphology. So to find gravitational wave signals from supernova, we just take multiple gravitational wave detectors. We look for excess power that occurs in those detectors at the same time, accounting for the speed of light between detectors. And then we look if the signal, the excess power that occurred at the same time has the same shape signal. So then this is an example here from this is Merrick's paper where he just shows the method for detecting supernovae. And this method, this unmodeled method of finding supernova signals is really not very sensitive at all. So over here is like some unrealistic supernova waveforms, and over here we get more realistic, and you can see that to have like a 50% detection efficiency for cold collapse supernova signals, you'd need like a signal to noise ratio of 20, which is pretty big. We don't want like a once in a lifetime supernova to occur and the signal to be there with signal to noise ratio of 15, and then we just miss it because our searches are not very sensitive. And these searches only give you estimates of the duration and the frequency, and that's fine, but we want to measure some more exciting astrophysical parameters of the source. So people like me who work in gravitational wave supernova land, we're trying to make better searches that actually take into account some of the features that we expect in supernova signals. And once we find it, we actually want to be able to say something about the source astrophysics other than the signal was half a second long and has a frequency of 800 hertz or something. So I can't talk about all the cool work we did in 10 minutes. So I'm going to talk about some study we did recently about trying to determine the explosion mechanism from the gravitational wave signal. So a typical cold collapse supernovae is thought to explode because it absorbed some of the energy from the neutrinos. So in this little diagram, this is your proto-neutron star here, and all these little arrows are supposed to represent the huge amount of neutrinos that are emitted. And in this region here, you start to heat up from the energy from the neutrinos, and you have lots of convection and this thing here called the standard accretion shock instability, which helps you to power a full supernova explosion. So this is kind of like the standard, although last week some people argued with calling this standard if you like jets and you know who I'm talking about. Yeah, so this is the standard way which most people think supernovae explode. And so this is what the gravitational wave typically looks like for these neutrino-driven explosions. So you have this rising frequency of time, and that's pretty well understood. We have several groups who make these universal relations that show how the gravitational wave frequency of that mode is related to the properties of the proton-neutron star. And yeah, even though the different groups' relations vary a little bit, they're all a pretty good description of how you can relate this mode to the parameters of the proton-neutron star. And then sometimes you also get this low frequency mode due to the standard accretion shock instability, and you can learn some things about the shock parameters from that. And then something that I see in my models is that at the time when the shock is revived, this low frequency mode starts to go away, and also the amplitude in my high frequency mode gets better. So maybe we can even say something about the shock revival time. But then if you go to other explosion mechanisms, like the magnetorotational explosions, we understand much less about what the gravitational wave signal should look like and how it relates to the properties of the source. So in the magnetorotational explosion mechanism, the magnetic fields help you translate some of the rotational energy into the shock wave and power a full explosion. And so they still have this rise in frequency of time that we saw in the neutrino-driven explosions, but at least in my simulations, the frequency gets a bit higher than the neutrino-driven explosions. And you can also get this, depending on your source angle, you can get this big spike t equals 0. Thus, the spike is bigger depending on how large your rotation is. So you can learn something about the rotational speed from that. But then the relations between this gravitational wave frequency and the properties of the proton-neutron star changes if you include magnetic fields and rotation. So our universal relations don't work anymore, and then we don't know how to say something about the source from these kind of explosions. So that's a thing to work on in the future. So up here, I have a bunch of papers already about how you can determine the explosion mechanism from a gravitational wave signal, but there was loads of problems with that. And the main problem was that we used these really old waveforms. So at the time that we did these studies, we had pretty good waveforms for the neutrino-driven explosion mechanisms. But then for magnetorotational explosions, we only had waveforms that went to 200 milliseconds. So if you, just this bit. And then we're trying to do model selection between this thing and this thing. So then, it's pretty obvious that we got like 100% because we were comparing one long thing to one little tiny thing, even though this is supposed to be long. And also because these waveforms ended before the shock had even revived in the supernova, we didn't even actually know if they did explode by the magnetorotational explosion mechanism because they hadn't even exploded at all by the time the simulation finished. And all of the neutrino-driven explosions just completely ignored rotation, but you can get rotation and a neutrino-driven explosion. So another question was like, did we just make a rotation or a non-rotation detector? But this was just the best that we could do at the time because that's all the waveforms that we had. But now the situation has changed a little bit. So Vishnu over there added some magnetic fields into Bernard supernova code. And so we were able to make some new long duration magnetorotational waveforms. So here's one of the ones that I made, and this goes up to 0.6 seconds. And then there's also a group in Spain, and they also have lots of magnetorotational simulations. And so I got in contact with them and said, can I have a bunch of your waveforms? And this is one of their waveforms. And for now, we have enough magnetorotational long duration waveforms that we can do the study again. And we also now have some good rotating neutrino-driven explosions, so we can see, we can make the length of the waveforms the same we can be a bit more sure if we've not made a rotation or non-rotation detector. And then just to make things hard for ourselves, we also added in a non-exploding class, so a bunch of supernova waveforms where the shock never gets revived. And we also added a not supernova class, so we just took some simple equation to make a gravitational wave signal that has the shape but isn't really from supernova. And then we used 3 different classification methods to distinguish between all these different explosion classes. They were Bayesian model selection, convolutional neural networks, and dictionary learning. And I put 0 details about any of those things in my presentation because there's no time. But you can see our paper if you care about that. And we used lots of the waveforms for training these algorithms and then kept a couple that we didn't use for the training to test. So here's a few more details. We used recolored noise. That means that I took the gravitational wave detector noise from the 3rd observing run and then changed the sensitivity of it so that it matched the sensitivity of these 3 noise curves for LIGO at design sensitivity, NEMO, which is the proposed high frequency Australian gravitational wave detector, and then Einstein telescope. So you keep all the horrible glitchy rubbish that's in the real gravitational wave detector noise, whether you get the future detector sensitivities. And we used a variety of signal to noise ratios and put the signals in the galactic center or the Large Magellanic Cloud. And then these were the results that I got for my method. So now that the signals look so similar, now that we have better gravitational wave signals, I was kind of expecting that this wouldn't work at all, and then we just have to write, yeah, our old work's rubbish and we can't even do this now. But it turned out a bit better than I thought. So at the bottom is the, if you get it right, you want it to be diagonal, and if it's not diagonal, then you've basically classified it wrong. But for these not a supernova waveform, we classified them 100% correctly. Then for the non-exploding models, these are pretty hard because most of the features that are different in the non-exploding and neutrino-driven explosion gravitational wave signals are at really low frequencies where LIGO isn't very sensitive. So for those ones, we only got 58% of them in the right class, and then most of them just got mixed in with the neutrino-driven explosions. But then for Einstein telescope, where it has better low frequency sensitivity, we got a 60% correctly classified. And then for NEMO, which has no low frequency sensitivity, we got 50%, which basically doesn't mean anything. They're wrong. And then for the neutrino-driven explosions, we got about 75% classified correctly in all the detectors. So I was really happy about that we managed to put the rotating neutrino-driven explosions in the correct class, and they didn't end up in with the magnetorotational explosions. And then we got between 75 and 80 for the magnetorotational explosions. So even though it's not 100% correctly classified like it was in our previous studies, now we have more realistic waveforms, and so our results are worse but more accurate, I would say. So yeah, here's my conclusions.
Thanks, Jade. Questions, Tegan?
Thanks for the interesting talk. I was wondering, for the not exploding and then not supernova, are they still astrophysical, or are they glitches basically?
So the not a supernova, we added it to the noise as if it was an astrophysical signal, but it's basically just a completely made up thing, like a random burst that looks supernova shaped. So that's not an astrophysical model. But for the non-exploding one, that is astrophysical. There is supernovae that they have a core bounce and then they don't have a full supernova explosion. Your star just disappears. Although it's kind of hard to tell from our simulations if sometimes it's possible that the shock would have revived if we had continued the simulation for longer, and we just think it was non-exploding because we ended it too soon. So you've got to be careful what models you define as non-exploding, but yeah.
Okay. Am I allowed to
Sure.
If you have the multi-messenger, does that let you constrain what the explosion mechanism is a lot better?
So I don't know if the neutrino signal would help us much, because I've never tried to do like a joint analysis between gravitational wave and neutrino results, but I guess we would certainly try.
Thank you.
One last question. Yeah, thanks for the interesting work. I was wondering, so you said that in the rotational explosions, you get typically higher frequencies. So do you understand from a physical point of view why that is the case? Is it related to a different contraction behavior of the protoneutron star, or what's the physical reasoning?
So it's possible that it's a physical reasoning, and it's also possible that it's because of our simulation setup, which I'm worried about. Yeah, so we didn't use full general relativity when we use the when we do the magnetorotational simulations, because we don't have the code that does full general relativity and magnetic fields yet. But in 2D, it shows that oh, microphone broke. Yeah, in 2D simulations, somebody's already showed that if you don't use full general relativity, that increases your gravitational wave frequency by 20%. But mine have definitely increased by significantly more than 20%. But I think really we should do that again in 3D just to make sure that you know, the increase wasn't because of that. So I hope that at least some of it is astrophysical, but I can't guarantee that it wasn't simulation setup.